Hello everyone, this lesson is about potential dividers. By the end of the lesson we're going to know what a potential divider is and how it can be used. We're going to know how it works and be able to explain different types of potential dividers, how they work, and be able to calculate values for resistance and potential difference in a potential divider circuit. Potential difference in circuits. What would be the potential difference across a resistor? We will assume that the cell has negligible internal resistance, and we can say that the cell has an EMF of 12 volts, and that 12 volts is applied across the circuit. We can then say the potential difference across our resistor is 12 volts. When we talk about potential difference, we're talking about a difference in potential between 2 points. So the potential at this point is 12 volts, and the potential at this point is 0 volts. And so we then measure with our voltmeter the difference in potential, which reads as 12 volts. If we look at the potential difference across a wire, it's helpful to think of the potential at different points along the wire. So our cell has an EMF of 12 volts. So what would the voltmeter read if the slider was all the way over to the right, for example, or if it was all the way over to the left? What would be the reading on the voltmeter in different places? So assuming we've got wires of negligible resistance, so there's no potential drop across those connecting wires, the wire that runs along the middle here is going to have a potential at one end of 12 volts and a potential at the other end of 0 volts. What would the potential be halfway along? We'd expect the potential to be 6 volts at a point midway along the wire. And if we were to take our voltmeter and move it to that point, so we were measuring between the 12 and the 6 potential values, we'd read a potential difference of 6 volts, 12 take away 6. If we just look at the potential values and how they vary as we move along the wire, the values vary smoothly as you move along from 12 volts down to 6 volts down to 0 volts. Plotting that on a graph of potential along the wire against length, we'd see a straight line that goes down to 0 like that. If we were to read the potential difference on the voltmeter, we'd see that that value gradually increases. It's a linear increase. The potential difference we're measuring with the voltmeter increases as the length of the wire increases, and that's because the difference in potential is increasing, the potential difference is increasing. This setup is actually used to give a variable output from our power supply. It's called a potentiometer. As you move the slider across, you increase the share of the total voltage, the 12 volts EMF, you increase the share of that is going to the output, and in that way you are controlling your power supply, so you can vary the output from 0 up to 12 volts. This is sometimes called a potentiometer. If we look at potential difference across components, you could probably look at that and think, oh, 2 equal resistors, 12 volts EMF, we're going to have 6 volts across each resistor, and that will be right. We can show that's the case. We can calculate the current through the circuit from the total potential difference divided by the total resistance. So 12 divided by 100 plus 100 in brackets 200 equals 0.06 amps. So we've got 0.06 amps through each resistor. We then use V equals I times R to find V1 and V2. So in both cases it's 0.06 times 100, which is 6 volts. So there we are, we've shown that we've got 6 volts dropped across each component when the resistor values are the same, and that's possibly what you predicted. So if we look at the potential at different points in the circuit, we can see on the left we've got a potential of 12 volts, and then across, as we go past the 100 ohm resistor, potential drops to 6 volts, and then as we go past the next resistor, it drops to 0 volts. So you can see that these two resistors connected together in series have split the potential, or divided it, so that we've got 6 volts across each one. So this is an example of a potential divider. Okay, question now for you to think about: what will happen if R1 is changed for a 200 ohm resistor? What will happen to the share of the power supply potential difference? How will it now be shared across the two resistors? So if we increase R1 to 200, we've now got a 200 ohm resistor in series with a 100 ohm resistor. You might be able to see that the 200 ohm resistor is going to have a bigger share now of the potential difference of the power supply. In fact, that is the case. It goes up to 8 volts, and the 100 ohm resistor has now got a potential difference of 4 volts dropped across it. So R2, it's still 100 ohms, but it's got a smaller potential difference across it. Let's show how we can calculate that. So the total resistance is 300 ohms. The current in the circuit is V over R total, 12 divided by 300, which is 0.04 amps. V1 is IR1, which is 0.04 times 200, which equals 8 volts. And V2 equals IR2, which is 0.04 amps times 100 ohms, which is 4 volts. So we've calculated that we would get 8 volts and 4 volts. In general, the bigger the resistor compared to the other one has the higher potential difference share, the higher share of the total potential difference across it. We know that the current in the circuit, I, equals V1 over R1, and that also equals V2 over R2. So if we were to rearrange V1 over R1 equals V2 over R2 to get V1 over V2, what would that equal? Let's pause the video and have a go at that. So what we get is V1 over V2 equals R1 over R2. And we can see from that the ratio of the potential differences, V1 to V2, is equal to the same as the ratio of the resistors, R1 to R2. Let's just check our example. Does that work? V1 to V2 is 8 over 4, which is 2. R1 over R2 is 200 over 100, which is also 2. So it works, and that's a helpful relationship. This, by the way, isn't given in the formula sheet, so it's a helpful one to learn. So practice using this relationship now. Calculate R1 if V2 equals 3 volts, V total equals 12 volts, and R2 equals 50 ohms, as shown in the circuit diagram. First thing we can do is find V1 from the difference between V total and V2, so that's 9 volts. We can now use the relationship V1 over V2 equals R1 over R2, so we'll put the values in. V1 over V2 is 9 over 3, and that's going to be equal to R1 divided by 50. We need to find R1. So from that, we find that R1 equals 150 ohms. We could look at it and think, well, V1 is 3 times bigger than V2, so therefore R1 needs to be 3 times bigger than R2. So 3 times 50 equals 150. So what is a potential divider? It's simply just a series circuit with 2 resistors. You don't need to show the power supply in a potential divider circuit. Very often they're drawn as shown here, with components connected between 2 rails, 0 volts and maybe a plus 12 volt rail, but it could be a different value. And that means that any components can be connected between the rails, and this is something that's used in electronics. The plus 12 volt rail we're going to refer to as our V total. We know that identical resistors would each have an equal share of V total. So if V total was 12 volts and we had identical resistors, we'd have 6 volts dropped across each resistor. But if one resistor is bigger, higher value of resistance than the other, the bigger resistor will get a greater share of V total across it. Question: find V2 if V1 is unknown. In this example, we can't use our ratio, R1 over R2 equals V1 over V2, because we have two unknowns. But what we do have is V total, so there is another method. We can also write V2 divided by V total equals R2 over R total. So the share of the potential difference across V2 as a ratio of the total is equal to the resistance of R2 as a ratio of the total resistance. So let's calculate V2 then. So V2 over 12, which is our total, V total, equals 2 over 6, which is the total resistance. We can calculate V2 from that. V2 equals 4 volts. In potential divider questions, V2 is often written as V out because it's an output which is going to be turning something on. V total is often written as V in. And so we arrive at the equation that's on the formula sheet, which is V out equals V in times R2 divided by R1 plus R2. And you can see that how that comes from the relationship we were just talking about, just expressed in terms of V out and V in. And this one is on the formula sheet. So we're going to look at some examples of potential dividers, and then there's some questions for you to have a go at. So this example, a thermistor is in series with a resistor to switch heating on when it is cold. Where would we connect the heater so that it switches on when it is cold? In other words, the V needs to increase when cold. Pause the video and have a think. So as it gets colder, R2 increases. Remember how a thermistor works. Resistance increases as it gets colder. And because R2 increases, V2 also increases. And this switches the heater on. So a greater share of the total potential difference is now shared or dropped across resistor 2. And because it's got a bigger potential difference across it, that can be sufficient to then switch the heater on. So that would be the correct place to draw the heater across the thermistor as shown. Where would you connect a fan to come on when it gets hot? So the correct position for the fan would be across resistor 1. As it gets hot, resistance R2 decreases, and so V2 decreases. This increases V1, the resistance, the potential difference across R1, and would switch the fan motor on if the motor was positioned there. Activity for you to try. Design a potential divider to switch on a street lamp when it gets dark. Hint, you'll need to use an LDR, a light dependent resistor. Explain how your circuit works. Pause the video and have a think about this for a few minutes. So the potential divider circuit would look something like this. You can see the resistor in series with the LDR and connected to a power supply of 12 volts. Where will you connect the lamp? So as it gets dark, the resistance of the LDR increases, a bigger share of V in is dropped across the LDR, this increases V out, and the lamp switches on. So the correct position is to connect the lamp across the LDR as shown. So just to model how the potential differences would or may vary. So when it's light, the resistance of the LDR is low, and it would have a lower share of the potential difference dropped across it. So typical values might be 3 volts across the LDR and 9 volts across the resistor. As it gets dark, the resistance of the LDR increases, and so a greater share of the V in is now dropped across the LDR, so that could go up to 6 volts, and you then have 6 volts across the resistor. So because we've got 6 volts across the LDR, that could now be sufficient to switch the lamp on if it was a 6 volt lamp. That shows you how as the resistance changes, the potential difference changes, and how that in turn can turn components on. So this is a question I'd like you to try writing the answer to. Draw a potential divider circuit with a thermistor. So you're going to have a resistor and a thermistor in your circuit. State and explain what happens to the potential difference across each resistor, so the fixed resistor and the thermistor, as temperature increases. Assume this is a negative type thermistor, so as we've just been talking about, the type where the resistance increases as it gets dark. Alright, so pause the video, have a go at that. It's a 4-mark question, so it will be 1 mark for the diagram, circuit diagram, and 3 points are going to be needed to explain what happens. So in your explanation you would need to say, when temperature goes up, resistance of the thermistor goes down. There is now a lower share of the total potential difference across the thermistor, and so the potential difference across the resistor increases. The 4th mark there is going to be for a correct diagram. So here are now some questions for you to try. Pause the video and have a go at these. So for the circuit at the top, calculate V2. So we call that V out. Is going to be equal to V in, which is V total, times R2 divided by R1 plus R2. So it's 12 times 400 divided by 500 equals 9.6 volts. So we're always going to get something that's less than the total voltage, 12, and we know that we're going to have 4/5 of 12, so that gives us 9.6. For the second circuit, calculate V2 when R equals 5 ohms, and then part 2, calculate the new V2 when R equals 8 ohms. We'll assume the temperature is constant in this question. It's a thermistor, but the temperature is constant. So second circuit, V2 when R equals 5 ohms is going to be equal to 6.7 volts. So it's V out equals V in times R2 over R1 plus R2. 10 times brackets 10 over 15, close brackets, equals 6.7 volts. Calculate the new V2 when R equals 8 ohms. Constant temperature. So let's just pause and think what we should get if we're increasing the resistance of R. That's going to increase the potential difference across R. V1 is going to increase, and so it should decrease V2, but let's see if that is the case from our calculation. Yes, indeed, we do find that as R increases, the variable resistor increases from 5 to 8 ohms. The potential difference across the thermistor drops from 6.7 volts to 5.5 volts. Temperature is constant here, so we assume the resistance of the thermistor stays constant. So in this circuit we have a potential divider with a variable resistor and a LDR, and we're given the resistances and V in. Will the lamp, which is rated at 6 volts, turn on? Pause the video and have a go at that. So we need to calculate V out, which is the potential difference across the LDR, and will also be potential difference across the lamp. And we need to see if that value of V out is 6 volts or more. If it is, then the lamp will turn on. So what we find here is that V out is 4.2 volts, so no. We found V out from V in, 9, times brackets R2 divided by R1 plus R2, 4.2 divided by 4.2 plus 4.8, and we get a value of 4.2 volts. So that's below the voltage that the lamp needs to turn on, so it won't switch on. What is the maximum variable resistor resistance needed? So we're going to turn the variable resistor resistance down, which would then increase the voltage dropped across the LDR, and that would then in turn increase the potential difference across it to give us 6 volts. So I want you to calculate the maximum variable resistor resistance needed. So to find this, we have to use our ratio method. So R1 over R2 equals V1 over V2. And we're trying to find R1 when V2 equals 6. So R1 over 4.2 equals 3 over 6. So we know that if V2 is 6, V1 must be 3, because added together they have to equal 9 volts. And then we can calculate R1, and that equals 2.1 ohms. So you can see that we've had to turn down the variable resistor from 4.8 ohms down to 2.1 ohms, which has in turn increased the potential difference across V2 to 6 volts, which is the level that is needed to switch the lamp on. So I'd like you to review your learning now and to just reflect on everything we've learned in this lesson. Success criteria. Can you explain potential difference as a difference in potential between points in a circuit, understanding that V total equals V1 plus V2, etc., and identifying different points around the circuit what the potential values would be. Do you know that a potential divider, what a potential divider is and how they can be used, e.g. to switch a heater on when cold? So examples were given and you designed a potential divider circuit as well. Can you explain how a potential divider works and predict what will happen if the values are changed? So that was a long answer question. You may need to go back and have another look at that. And can you calculate values for R and V in a potential divider circuit using the equation V out equals V in multiplied by R2 over R1 plus R2. So well done if you've got all of that. You can go back and have another look at anything you are less sure about. Thank you very much for watching.